Let's talk about particular solution. In the previous video, we talked about this question here. This was the homogeneous problem where our input was 0, but now our input has something else right here. So our right hand side is the input and left hand side is the filter. By the way, y1 is a constant. You might be confused by this new wording, the filter and the input. So let me explain. Everyone knows this equation. So we can say x is our input and y is our actually output. But if we, for example, put something else, let's say 5y here, then this is kind of our filter. It's not the best example that I can give, but to make it more understandable, I can try to give this example. So here, our output is still y, but this whole thing is the filter. And the right hand side is our input, like x. And we have to do some math to extract the y from here and then get our output. That's essentially our goal. Like right here, when we did in grade, I don't know, 6 or 5, we sent the 5 on the other side and then now we have our output, y. We are essentially doing the same here, but more complicated math, I guess. You might be asking what then goes to the right hand side and what goes to the left hand side. The filter side, left hand side is made of y's and right hand side, the input is made of t's. Exactly like this example where left hand side is the y and then right hand side is the x. Okay, then what should we do at this point? In the previous video we solved for y homogeneous and now we are going to solve for y particular. So to define things better, now we can separate these things. And now if you separate the equations, you will see this. And so we get these two equations. And after we solve for both y particular and y homogeneous, then we add them together and then we get the solution, y. Okay, so let's do that then. I'm just gonna go through the homogeneous part fast because we did this in the previous video. And so we find our process time constant from here. And so we find the y homogeneous to be this. And we know this is stable because it decays. And PTC was the time when the output was getting to its 1/3 of its value. It's actually 1 to the e of its value, but we can just say approximately it's 1 divided by 3. And for particular solution, we will make a guess. So we will say it will equal to e to the minus t divided by alpha. But I have to mention that this is not a guess. For homogeneous, it's always like this. It never changes. But for particular solution, you have to guess. I will show how we guess. And let's just go through the route of verifying it. So for the inputs that have the e format, like e to the power of something, you're basically writing down the same thing times a constant. And that constant, we don't know what it is yet. At the end of the calculations, we will find the constant. So let's calculate. If we take the derivative of our guess, it will be tau divided by alpha times e. Because if we take the derivative, it's minus e divided by alpha times e to the minus t divided by alpha. So this alpha comes down and the minus also comes down and we had this e in front. And in the actual equation, because we had a tau here, that goes there. And now we equate coefficients. As you can see, these are all equal. So maybe I can just color them. Do not cancel out like this. This is a really bad idea. I know it's gonna be the same for this situation, but just keep in mind that you don't cancel out and you just equate coefficients. I showed why that was important in the previous video. And let's now equate coefficients. And this is the solution we find for E. Simplified a little bit more, we can write it like this. Just multiply everything by alpha and you get basically the other. And our y particular then now is this. And now you might notice that it's stable because it decays, and this is our E. You might have some questions in your head. So we guessed this and we did solve it. So like, how do we know this guess was kind of right? This thing is the proof that our guess is right, because if this red part was not the same, then how else you want to equate this, you know? We already had this part as input, and we had to make y particular something that was gonna make this equation possible. And the only way is to have the exact same e to the power of something exactly as this. So then when we put it on the left hand side, we get the same thing, and then it's equal. And something really good about the e is that when you take the derivative of it, it doesn't change. So we took the first derivative of y particular, but it didn't change, so it stayed the same, and the equation is now possible. You might have questions in your head that what if now then we didn't have e to the power of something and something else. And in the next video I will show that how the guess process works. But for now, let's just continue with this problem. So we got these two solutions, and now let's write the general solution. And so this part is our particular, and this part is our homogeneous. Okay, so why does this called general solution? It's because we don't know d. This becomes like a general solution. So we don't exactly know how this output will be, because let's say you give this 10, you get a different value than when you give this 100. So you have to find what is d, the constant. And so we then have something else, particular solution. This is when our question states that what is the initial condition. So I didn't define it here, but let's say at y equals 0, our actual value of y is y naught. So then we can solve for that, like right here from this one. And when we put 0 for t, the e becomes 1, and we are left with this. And after we rearrange stuff, then we find d to be y naught minus alpha y1 divided by alpha minus tau. And so let's rewrite. So now this is our particular solution, and the question is done. You can also simplify this a little bit more, just rearranging a little bit. Okay, you might be wondering then, what is the graph of this? How does this look like? We talked about transients in the previous video and those kind of stuff. Okay, let's graph this in Desmos, and I'm just going to use this format, and we have to define what we're going to use this for, this constants. Let's say 1, 2, 1 and 0.1 for tau. So we are picking a tau value that's like kind of smaller than alpha, so we can see the behavior of the exponentials easier. Okay, let's see the homogeneous solution. So this is our homogeneous solution, and yeah, it's a transient and it decays quite fast. It's gone by the time we reach like to 1 or even before that. And let's look at our particular solution, and it lasts a little bit longer. As you can see, I think we can no longer see it around 5 or 6, and the reason why this lasts longer is because of the power. The particular solution has t times to the 1, and the homogeneous one has t divided by 0.1. So PTC of homogeneous solution is much smaller than PTC of particular solution. So particular solution decays slower, but a homogeneous one decays faster. When you add them together, then we get this red function, which we see this interesting behavior. So if we look at the actual function, the red one, we can say that the homogeneous solution transient is kind of done by this point. Like after, when we reach this point, the homogeneous solution is like almost gone, and now we are kind of only having the particular solution in this section, which is why the green is covering the red like perfectly. And vice versa, if we had the particular solutions PTC smaller, then particular solution would have died faster and we would have saw something else. Thank you for watching. In the next video, we are going to talk about how to guess the particular solution and also about the duplication problem.